For as long as humans have looked up at the sky, one question has quietly lingered in the background. Why is our home, Earth, a round sphere, while the galaxy we live in is a thin, flat disk stretching across the cosmos? It feels like a contradiction. If gravity pulls everything inward, shouldn't everything be round? Why does one rule shape planet, while a completely different rule shapes galaxies? And here is the twist. The answer reveals one of the strangest, most overlooked truths about the universe, that the forces shaping our world are not the same forces shaping our galaxy. In fact, the reason the Milky Way is flat is tied to something Earth doesn't have enough of, and something our galaxy has far too much of. So get ready, because the answer is not just science. It is a journey into the invisible forces shaping the entire universe and the surprising physics that make our cosmic home far stranger than it first appears. If you love the content, leave a like and subscribe to the channel. We begin. When you look up at the night sky on a clear evening, you're witnessing one of the universe's most curious patterns. The Earth beneath your feet is a sphere, our moon hanging above is a sphere, the sun that warms us is a sphere. Yet when you zoom out and look at the bigger picture, the Milky Way galaxy we call home is shaped like a massive cosmic disk, spinning slowly through the void. Our entire solar system, with all its planets and asteroids, is arranged in a flat disk around our star. Even the most extreme objects in the universe, the violent maelstroms of matter spiraling into black holes that we call quasars, take the form of brilliant, glowing disks. It's almost as if the universe is working from a remarkably limited playbook, choosing between just two basic shapes to build everything we see around us. This isn't some cosmic coincidence or quirk of observation. The universe isn't being lazy or uncreative. Instead, this pattern reveals something profound about the fundamental laws that govern reality itself. Every planet, every star, every galaxy, and every swirling cloud of cosmic gas is following the same set of universal rules, bound together by the same invisible force we call gravity. Yet somehow, from these identical starting conditions and identical physical laws, nature produces these two distinctly different shapes. Understanding why this happens, why gravity sometimes builds perfect spheres and other times constructs vast spinning disks, will take us on a journey through some of the most fundamental concepts in physics. We'll need to understand equilibrium, the delicate balance of forces that determines when something stops changing. We'll need to grasp symmetry, not just as a concept of visual beauty, but as a deep principle that shapes the very fabric of our universe. And we'll need to recognize how these two concepts work together, like invisible architects, to determine the final form of everything from the smallest moon to the largest galaxy. Let me start by introducing you to the concept that engineers live and breathe every single day of their professional lives: equilibrium. If you've ever looked at a bridge and marveled at how it stays up, you've witnessed equilibrium in action. Take a moment to really think about what a bridge is doing. Every single brick in that structure, every steel cable, every bolt and rivet is experiencing forces. Gravity is pulling everything downward with relentless consistency. The traffic moving across the bridge adds even more weight, creating additional downward forces that pulse and change throughout the day. The wind pushing against the sides of the bridge creates lateral forces, trying to push the whole structure sideways. Temperature changes cause the materials to expand and contract, creating internal stresses that try to pull things apart or push them together. Despite all of these forces working in different directions, pulling and pushing with different strengths, the bridge doesn't collapse. It doesn't twist itself into a pretzel or crumble into a pile of rubble. It stays exactly where it is, maintaining its shape day after day, year after year. This is because engineers have carefully designed every component so that all of these forces perfectly balance each other out. The tension in one cable is matched by compression in a support beam. The downward gravitational pull on one section is countered by the upward push from the foundations. Every force has an equal and opposite force working against it, and when you add up all the forces acting on any given part of the bridge, they sum to zero. This is mechanical equilibrium, the state where all forces are balanced and nothing changes. But here's something fascinating that most people never think about when they look at a bridge. Even the concept of downward isn't as simple as it seems. Consider the Verrazzano Narrows Bridge in New York, a magnificent suspension bridge that spans about 4 miles across the entrance to New York Harbor. When engineers designed this bridge, they couldn't simply treat downward as a single consistent direction across the entire length of the structure. Why not? Because the Earth isn't flat, it's curved. The direction that we call down, the direction gravity pulls, is actually toward the center of the Earth. On the western end of the bridge, down points toward one spot in the Earth's core. On the eastern end, down points toward a slightly different spot in that same core. Over a distance of 4 miles, the curvature of the Earth is significant enough that these two down directions actually diverge from each other by a measurable angle. If the engineers hadn't accounted for this, if they'd treated the entire bridge as though it existed on a flat plane with a single consistent downward direction, the forces wouldn't balance properly. The towers supporting the bridge would be slightly misaligned, the cables would be under uneven tension, and over time these small imbalances would accumulate and cause structural problems. So they had to factor in Earth's curvature into their calculations, ensuring that every component was positioned and reinforced to handle the actual direction of gravitational pull at its specific location. This might seem like an obscure detail, but it perfectly illustrates a crucial principle. When forces aren't in equilibrium, when they don't balance out to zero, shapes change. Things move, structures deform or collapse. But when equilibrium is achieved, when all forces cancel each other out, shape becomes fixed and stable. This brings us to the second fundamental concept we need to understand: symmetry. Now, when most people hear the word symmetry, they think about visual patterns. A butterfly's wings are symmetric. A human face is roughly symmetric down the middle. A snowflake has six-fold rotational symmetry. These are all examples of geometric symmetry, patterns where one part of an object mirrors or repeats another part. But in physics, symmetry means something deeper and more powerful. It's not just about how something looks. It's about how something behaves when you transform it in some way. Does it stay the same? Does it change? And if it changes, how does it change? Let's start with the symmetries of the shapes we're trying to understand. Planets and stars have what we call spherical symmetry. What does this mean? Imagine you're holding a perfect sphere, maybe a basketball or a globe. Now imagine rotating that sphere in any direction, any angle, around any axis passing through its center. No matter how you rotate it, the basic shape remains exactly the same. You can't tell that you've rotated it just by looking at its outline. This is spherical symmetry, a property that's the same in all three spatial dimensions. You can rotate it left to right, up and down, or any diagonal direction in between, and the fundamental shape doesn't change. Now contrast this with disc-shaped objects like galaxies and solar systems. These have a different kind of symmetry called circular or cylindrical symmetry. If you take a disc and rotate it around the axis that passes through its center perpendicular to the flat surfaces, The disk looks the same after the rotation. Spin a vinyl record on a turntable, and every frame of that spinning motion looks like every other frame. But if you try to rotate a disk around any other axis, it immediately looks different. Tilt a disk on its edge, and you can tell instantly that you've rotated it. So disks have symmetry around one axis, but not around others. They're symmetric in 2 dimensions within the plane of the disk, but the third dimension, the direction perpendicular to that plane, is special and different. Now here's where things get really interesting. I just described the symmetries of shapes, the geometric objects themselves, but forces can also have symmetry. And this is where the magic happens, where we start to see why the universe builds what it builds. The symmetries of the forces that create an object determine the symmetry of that object's final shape. Let me say that again because it's crucial. The symmetries of the forces determine the symmetries of the shapes they create. When you're building something out of balanced forces, the final form you end up with will reflect the symmetries inherent in those forces. For all of the really large structures in space, the structures we're trying to understand, one force dominates above all others: gravity. Gravity is what holds planets together. Gravity is what keeps stars from flying apart. Gravity is what binds galaxies into coherent structures instead of letting them dissipate into the void. So if we want to understand why space objects have the shapes they do, we need to understand the symmetry of gravity itself. For our purposes here, we don't need to think about gravity the way Einstein did, as a warping of the fabric of space-time itself. That's a more accurate description, but it's also more complex than we need. Instead, we can use Isaac Newton's classical understanding of gravity as a force, and that will be perfectly sufficient to explain what we're after. Newton's universal law of gravitation tells us something fascinating about how gravity works. The strength of gravitational attraction between 2 objects depends on 2 things: their masses and the distance between them. Specifically, the force is proportional to the product of the 2 masses and inversely proportional to the square of the distance between their centers. That inverse square law is crucial. If you double the distance between 2 objects, the gravitational force between them doesn't just get cut in half. It drops to 1/4 of what it was. Triple the distance, and the force drops to 1/9. This rapid fall-off with distance is characteristic of inverse square forces, and it has profound implications. But here's the key insight for our discussion of symmetry. Gravity drops off at the same rate in all directions. If you're standing at some fixed distance from a massive object, say you're floating in space 1,000 kilometers from the center of a planet, the gravitational pull you feel doesn't depend on which direction you approached from. It doesn't matter if you came from the north, the south, the east, the west, or any diagonal direction in between. As long as you're at that same distance from the center of mass, the gravitational force has exactly the same strength. If you mapped out all the points in space where the gravitational field has some particular strength, you'd find that those points form a sphere around the source of gravity. This is what we mean when we say gravity has spherical symmetry. It exerts its influence equally along all 3 spatial dimensions. It doesn't favor any particular direction over any other direction. This dimensional egalitarianism, this complete lack of preference for any particular direction in space, is also shared by another effect that turns out to be crucial for understanding why planets and stars are spherical. But before I tell you what that other effect is, let's dive deeper into the specific case of planets. Let's talk about the Earth, the ball of rock we're all standing on right now. The Earth is definitely a sphere, or at least it's extremely close to being a perfect sphere. We'll talk about the small deviations later, but first let's understand why it's spherical at all. The Earth is held together by its own gravitational field, the same field that keeps me stuck to the surface and prevents me from floating off into space. And just as conveniently as gravity keeps me on the surface, the ground beneath my feet keeps me from plummeting downward into the molten core. Think about what's happening beneath your feet right now. There's a chunk of rock directly below you, supporting your weight. That chunk of rock is itself supported by another chunk of rock beneath it, which is in turn supported by yet another chunk beneath that. We can imagine this as a tower of blocks, like a column of Minecraft blocks if you're familiar with that game, extending all the way down through the crust, through the mantle, all the way to the center of the Earth. The topmost block in this tower has to support your weight. The block below that has to support both your weight and the weight of that first block. The block below that has to support all three weights stacked above it, and so on, all the way down. As we go deeper into the Earth, each successive block is bearing more and more weight from all the blocks piled above it. The downward crush of all that accumulated weight is enormous. So why doesn't everything just compress down into a tiny, super dense point at the center? Because rock, like most solid materials, resists being compressed beyond a certain point. There's a fundamental property of matter called compressive strength, which describes how much squeezing force a material can withstand before it starts to deform. When you squeeze a block of rock, the atoms and molecules that make it up are pushed closer together. But atoms don't like to overlap. The electron clouds surrounding each atom repel the electron clouds of neighboring atoms. This electromagnetic repulsion provides an outward push that counteracts the inward squeeze. This is what we call pressure, and pressure acts outward in all directions from any given point. So we have two forces at work in our tower of blocks. Gravity pulls downward, trying to make everything collapse toward the center. Pressure pushes outward in all directions, including upward, resisting that collapse. A block located roughly halfway to the center of the Earth, about 3,000 kilometers down, experiences the downward gravitational pull from all the mass above it. This pull is trying to crush it downward, but that same block also exerts pressure, pushing upward against the block above it with enough force to support the weight of 3,000 kilometers worth of rock. The block immediately below our halfway point block is under even more pressure because it has to support one additional block's worth of weight. It has to hold up 3,001 blocks instead of 3,000. This creates what's called a pressure gradient, a smooth change in pressure as you move through the material. Pressure increases as you go deeper because each successively deeper layer has to support more weight above it. And it's this pressure gradient that creates an upward force that exactly balances the downward gravitational force. We can think of the entire planet as being composed of a huge number of these block towers, each one extending from the surface down to the core, each one in perfect equilibrium between the downward pull of gravity and the upward push of the pressure gradient. Each tower is responsible for supporting only itself, preventing its own collapse. But here's the question that should be bothering you right now. If each tower only needs to maintain its own up-down equilibrium, why do all these towers have to arrange themselves into a sphere? You could imagine building a flatter, disc-shaped planet by making some towers taller than others. Make the towers around the equator really tall and the towers near the poles shorter, and you'd end up with something that looks more like a disc or a flattened spheroid than a sphere. Each individual tower would still be in equilibrium in the up-down direction, with pressure balancing gravity along its length. So why doesn't this work? Why can't planets be disc-shaped? The answer is that up and down aren't the only directions in which forces are acting. We've been treating our Minecraft block towers as though they're completely independent of each other, as though each tower is isolated and only has to worry about its own internal balance. But that's not reality. Remember what I said about pressure? Pressure doesn't just push in one direction, it pushes in all directions equally. And this is where pressure shares the same symmetry property as gravity. Just as gravity pulls toward the center with equal strength in all directions, pressure pushes outward from any given point with equal strength in all directions. This means that any given block in our imaginary tower isn't just pushing upward on the block above it. It's also pushing sideways on the neighboring towers. Now, in the case of a perfectly spherical planet, this sideways pushing isn't a problem. Consider any block at a specific depth below the surface, say 3,000 kilometers down. This block is pushing sideways on all of its neighbors with a force determined by the pressure at that depth. But here's the key. All of those neighboring blocks are at exactly the same depth, because in a sphere, every point at a given distance from the center is at the same depth below the surface. Since they're all at the same depth, they're all at the same pressure. So our block pushes on its neighbor to the north with the same force that the northern neighbor pushes back. It pushes on its neighbor to the east with the same force that the eastern neighbor pushes back. All the sideways forces cancel out perfectly. Everything is in equilibrium, not just in the vertical direction, but in all horizontal directions as well. But now consider our hypothetical flattened disc-shaped planet. Pick a block somewhere in the thick equatorial region where we've made our towers tall. This block is, let's say, 5,000 kilometers below the equatorial surface. Now look at a neighboring block in an adjacent tower that's tilted slightly toward the pole. Because our planet is flattened, because the towers get shorter as you move from equator to pole. This neighboring block is at a different depth below the surface compared to our first block. It might only be 4,000 kilometers below the surface at its location. Even though the two blocks are at the same distance from the center of the planet, and therefore experience the same gravitational pull, they're at different depths below their respective surfaces, and therefore they're at different pressures. The block closer to the equator, which is deeper below the surface, is under higher pressure. It has more mass stacked above it. So when these two blocks push against each other sideways, the forces don't balance. The equatorial block pushes harder on its poleward neighbor than the poleward neighbor pushes back. There's a net sideways force directed away from the equator and toward the pole. This unbalanced force means the system isn't in equilibrium. Something has to move. The material near the equator will be squeezed outward and upward, while material near the poles will be pushed outward and downward, until finally every point at a given distance from the center is at the same pressure. And when that happens, when the pressure depends only on distance from the center and not on direction, the planet has become spherical. Now, you might object to this whole argument by pointing out that I've been assuming a planet made of separate, discrete blocks when real planets aren't made that way. The Earth is made of solid rock, at least in its crust and much of its mantle. Shouldn't solid rock be strong enough to resist these sideways forces? Shouldn't the structural integrity of the rock itself be enough to maintain a non-spherical shape, even in the face of unbalanced pressure forces? This is a good objection, and the answer reveals something interesting about the properties of materials. Rock is incredibly strong when you try to compress it directly. The compressive strength of typical rock is enormous, often in the range of hundreds of megapascals. This means you can stack an enormous amount of weight on top of rock before it starts to crumble and fail. However, rock has a weakness, and that weakness is its shear strength. Shear forces are sideways forces that try to slide one layer of material past another layer, or try to deform the material in directions perpendicular to the main compression. Think about trying to snap a stick. You're not compressing the stick straight on, You're bending it, applying forces that try to slide the fibers of wood past each other. That's a shear force. The shear strength of rock, its ability to resist these sideways deformations and sliding motions, is typically about 10 times lower than its compressive strength. So even though rock can support enormous vertical compression, it's much more vulnerable to sideways forces. When a rocky planet experiences the kind of unbalanced sideways pressure forces we've been discussing, the rock doesn't just sit there resisting indefinitely. Instead, it fractures. Cracks form, allowing the rock to break and shift. Entire layers can slide past each other. And through this process of fracturing and shifting and settling, the planet gradually reshapes itself into a more spherical form where the sideways forces are balanced. This process doesn't happen overnight. It can take millions or even billions of years, depending on the size of the body and the strength of the forces involved. But given enough time, gravity always wins, pulling everything into the most stable configuration, which is a sphere. And it turns out we can actually determine when an object is large enough for its own gravity to overcome the structural strength of its material and force it into a spherical shape. For rocky bodies, this threshold is reached when the object is several hundred kilometers in diameter. Below this size, a rocky body can maintain an irregular, lumpy shape because its structural strength is sufficient to resist the gravitational forces trying to reshape it. Above this size, gravity dominates and the body becomes spherical. We can see this transition clearly in our own solar system. Consider the asteroid Vesta, one of the largest asteroids in the main asteroid belt. Vesta has a diameter of about 578 kilometers, and when we sent the Dawn spacecraft to study it up close, we found that Vesta is decidedly lumpy. It's roughly spherical if you squint, but it has significant irregularities, large craters, and even a huge mountain near its south pole. Vesta simply isn't quite large enough for its gravity to have completely overcome the structural strength of the rock it's made of. Now compare this to Ceres, another large object in the asteroid belt, but one that's significantly bigger than Vesta. Ceres has a diameter of about 940 kilometers, and it is spherical. Its gravity is strong enough that any lumps or irregularities have been smoothed out over geological time, pulled into the stable equilibrium shape of a sphere. Now, I've been talking about rocky planets, but what about stars? Stars are very different from planets. They're not made of solid rock or liquid iron. They're made of plasma, ionized gas so hot that atoms are stripped of their electrons. And stars don't maintain their shapes through the structural strength of solid material. Instead, they maintain their spherical shapes through a different kind of equilibrium, but one that involves the same principle of balance forces. The force that prevents a star from collapsing under its own gravity isn't pressure from solid material resisting compression. Instead, it's pressure from the intense heat and radiation generated by nuclear fusion in the star's core. In the center of a star like our Sun, hydrogen atoms are being fused together to form helium, and this process releases enormous amounts of energy. This energy works its way outward from the core through various processes, creating an outward flow of heat and radiation. This outward flow creates pressure, pushing outward against the inward pull of gravity. The star exists in what's called hydrostatic equilibrium, a balance between gravitational collapse and thermal pressure support. If gravity were stronger, it would compress the star, which would make the core hotter, which would speed up fusion, which would create more pressure, pushing back against the compression. If the pressure were too strong, it would make the star expand, which would cool the core, which would slow down fusion, which would reduce the pressure, allowing gravity to pull things back in. The star naturally settles at a size where these forces balance, And just like the pressure in a rocky planet, the thermal pressure in a star is spherically symmetric. It pushes outward equally in all directions. Combined with the spherically symmetric inward pull of gravity, this creates a stable spherical shape. Stars like our Sun are actually extraordinarily spherical, much more perfectly spherical than the Earth or any planet. The Sun's equatorial diameter is only about 10 kilometers larger than its polar diameter, out of a total diameter of about 1.4 million kilometers. That's a difference of less than 1 part in 100,000. The Sun is, for all practical purposes, a perfect sphere, and it maintains this beautiful spherical symmetry for billions of years, a testament to the perfect balance of spherically symmetric forces. But wait, there's something I haven't mentioned yet, something that should make you suspicious of this entire explanation. Both the Earth and the Sun rotate. The Earth spins on its axis once every 24 hours. The Sun rotates once every 25 days or so at its equator. And rotation introduces a new force into our careful balance, the centrifugal force. Actually, centrifugal force isn't a real force in the technical sense. It's what we call a fictitious force or a pseudo-force, an apparent force that emerges when you're in a rotating reference frame. But from the perspective of someone standing on the surface of the Earth, or a blob of plasma on the surface of the Sun, centrifugal force is very real. It's the force that seems to push you outward when you're on a spinning merry-go-round, the force that makes water climb up the sides of a bucket when you spin it around. This centrifugal force acts in the opposite direction to gravity. While gravity pulls everything toward the center, centrifugal force pushes everything away from the axis of rotation. And here's the crucial point. Centrifugal force is not spherically symmetric. It's strongest at the equator, where points on the surface are moving fastest due to the rotation, and it decreases as you move toward the poles, dropping to zero right at the poles themselves, which sit on the axis of rotation and aren't actually moving in circles at all. This means that the total force acting on material, the combination of gravitational pull and centrifugal push, is different at the equator than at the poles. The effective gravity is weaker at the equator because some of the gravitational pull is being counteracted by the outward centrifugal push. This should allow you to build taller towers at the equator while still maintaining equilibrium. And indeed, this is exactly what happens. The centrifugal force from Earth's rotation does cause the planet to bulge slightly at the equator, creating exactly the kind of flattened spheroid shape that we said earlier would be unstable if there were no other forces at work. The question is, how significant is this effect? Let's do the calculation for Earth. At the equator, the upward acceleration you experience due to Earth's rotation, which we perceive as centrifugal force pushing us outward, is about 0.03 meters per second squared. Now compare this to the downward acceleration of gravity, which is 9.8 meters per second squared. The centrifugal acceleration is only about 0.3% of the gravitational acceleration. This means that the effective gravity at the equator is about 0.3% weaker than the gravitational pull at the poles, where there's no centrifugal effect at all. And when we look at Earth's actual shape, we find that it matches this prediction almost exactly. The equatorial radius of the Earth is about 6,378 kilometers, while the polar radius is about 6,356 kilometers. That's a difference of roughly 22 kilometers, which is about 0.3% of the total radius. The Earth is flattened by exactly the amount we predict based on its rotation rate. But that flattening is so small that Earth is still overwhelmingly spherical. If you held a scale model of Earth in your hand, even a very precise one, you wouldn't be able to see the flattening with your naked eye. You'd need to make precise measurements to detect it. So to summarize what we've learned so far, planets and stars are spherical because the forces that determine their shapes, gravity pulling inward and pressure pushing outward, both have spherical symmetry. They act equally in all three spatial dimensions. Rotation does introduce an asymmetry, a direction-dependent force that causes some flattening, but for objects like Earth and the Sun, the rotation is slow enough that this effect is small, and they remain nearly perfect spheres. The symmetries of the forces determine the symmetries of the shapes, and spherically symmetric forces create spherical shapes. Now let's completely change gears and talk about objects that aren't spherical at all. Let's talk about spiral galaxies like our Milky Way, about solar systems with their planets orbiting in a flat disk around the central star, about the dramatic accretion disks of glowing gas that spiral into black holes and neutron stars, and about the massive disks of material that surround newly forming stars. All of these things are flat and disk-shaped. They have circular symmetry, not spherical symmetry, and yet all of these things are governed by exactly the same force that makes planets and stars spherical. They're all held together by gravity. So what's different? Why does gravity sometimes build spheres and sometimes build disks? The key difference isn't in gravity itself. Gravity is always present, always pulling with spherical symmetry. The difference lies in what effect is resisting that gravitational collapse. For planets and stars, as we've seen, the resistance comes from pressure, either the pressure of compressed solid material or the pressure from thermal energy and radiation. And pressure, as we've discussed, is spherically symmetric, pushing outward equally in all directions. But for these larger structures, these galaxies and solar systems and accretion disks, the resistance to gravitational collapse comes from a different source: orbital motion. And orbital motion has a completely different symmetry. It has circular symmetry, not spherical symmetry. And this difference in symmetry is what produces the difference in shape. Let me walk you through the process of how a disk forms, and you'll see exactly what I mean. Imagine a vast cloud of gas and dust floating in interstellar space. These clouds really exist. We can see them with telescopes, dark patches that blot out the stars behind them, or sometimes glowing regions where nearby stars illuminate the gas. These clouds are huge, often dozens or hundreds of light years across, containing enough material to make thousands or even millions of stars. But they're also incredibly diffuse, spread so thin that they barely feel their own gravity. A typical interstellar cloud might have a density of just a few hundred atoms per cubic centimetre. For comparison, the air you're breathing right now has about 10 to the 19 molecules per cubic centimetre. So these clouds are far, far more tenuous than the best vacuum we can create in laboratories on Earth. Because the cloud's gravity is so weak, it takes an incredibly long time for it to start collapsing. We're talking about millions of years for any noticeable change to occur. But eventually, perhaps triggered by the shock wave from a nearby supernova or by the gravitational influence of a passing star, some region of the cloud becomes just a tiny bit denser than the surrounding regions. And once you have a density difference, gravity starts to do its work. The denser region has stronger gravity, which pulls in more material from the surroundings, which makes it denser still, which strengthens the gravity even more. It's a runaway process, a positive feedback loop that slowly, inexorably, causes the cloud to collapse in on itself. But here's the thing, these clouds aren't perfectly still. Nothing in space is truly motionless. Even if the cloud as a whole isn't rotating much, different parts of it will have slightly different velocities, moving in slightly different directions. Maybe one side of the cloud is moving a little bit faster than the other side due to the motion of the stars and gas clouds that passed through this region billions of years ago. Maybe the cloud formed from the merger of several smaller clouds that had different velocities. The point is, there will always be some net rotation, some overall spin to the cloud, even if it's incredibly slow. And this is where things get interesting, because as the cloud collapses, as it gets smaller and denser, something happens to that rotation. It speeds up dramatically. This speed up is due to one of the most fundamental conservation laws in physics, conservation of angular momentum. Angular momentum is a property that measures how much rotational motion something has, and it depends on three things: the mass of the rotating object, how fast it's spinning, and how far the mass is distributed from the axis of rotation. The crucial point is that angular momentum is conserved in the absence of external torques, which means that if you change one of these factors, the others have to change to compensate. If you bring the mass closer to the axis of rotation, decreasing the distribution radius, then the rotation speed must increase to keep the angular momentum constant. You've probably seen this principle in action, even if you didn't realize what you were looking at. Watch a figure skater performing a spin. They start with their arms extended, spinning at a moderate rate. Then they pull their arms in close to their body, and suddenly they're spinning much faster, becoming almost a blur. They haven't done anything to make themselves spin faster. No external force has pushed them into a quicker rotation. But by bringing their arms closer to their axis of rotation, they've decreased their moment of inertia, and conservation of angular momentum demands that their rotation rate increase to compensate. It's the same principle at work in our collapsing gas cloud, just on an enormously larger scale. When the cloud starts collapsing, when the gas and dust starts falling inward toward the center, the rotation speeds up. What might have started as an almost imperceptibly slow rotation, taking millions of years for one complete revolution, becomes faster and faster as the collapse proceeds. And as the rotation speeds up, something important happens. The centrifugal force becomes significant. Remember, centrifugal force is the apparent outward push you feel when you're rotating. It gets stronger the faster you're rotating and the farther you are from the axis of rotation. In the early stages of collapse, when the rotation is very slow, the centrifugal force is negligible compared to gravity, and the cloud collapses equally in all directions. But as the rotation speeds up, the centrifugal force grows stronger, and eventually it becomes strong enough to matter. Now, here's the crucial asymmetry. Centrifugal force only acts in one direction. It pushes outward, away from the axis of rotation, but it doesn't push along the axis of rotation at all. Think about that spinning figure skater again. The centrifugal force makes their arms want to fly outward, away from their body, perpendicular to the axis of spin. But it doesn't make their head want to fly off in the direction of their axis of spin. Centrifugal force acts only in the plane perpendicular to the rotation axis. This means that while centrifugal force can resist the gravitational collapse in directions perpendicular to the rotation axis, it does nothing to resist collapse in the direction parallel to the rotation axis. So here's what happens to our collapsing gas cloud. In the directions perpendicular to the axis of rotation, in what will become the plane of the disk, the gas and dust are trying to fall inward toward the center. But they're also orbiting around that center, and as they fall inward, they orbit faster and faster due to conservation of angular momentum. Eventually, the centrifugal force from this orbital motion becomes strong enough to balance the inward pull of gravity in these directions. The gas can't fall any closer to the axis of rotation because it's orbiting too fast. Every time gravity tries to pull it inward, the orbital motion carries it past the center, keeping it at a roughly constant distance from the rotation axis. But in the direction parallel to the rotation axis, perpendicular to what will become the disk plane, there is no centrifugal force to resist gravity. The gas in this direction isn't orbiting around anything, It's just falling straight down toward what will become the midplane of the disk. And so the collapse continues in this direction without any resistance from centrifugal force. The cloud flattens as it collapses, getting thinner and thinner in the direction perpendicular to the disk, while maintaining its extent in the direction parallel to the disk. Eventually, it settles into an equilibrium configuration, a flat, spinning disk. In this disk, every parcel of gas has reached a balance. In the plane of the disk, gravity pulling inward is balanced by the centrifugal force from orbital motion pushing outward. In the direction perpendicular to the disk, gravity pulling toward the midplane is balanced by pressure pushing upward and downward from the midplane. The disk has a small thickness, typically much smaller than its radius, determined by how much pressure support there is perpendicular to the disk plane. But the overall structure is flat, with all the material orbiting in roughly the same plane around the center. And this is why we see disks instead of spheres whenever orbital motion is the dominant effect, resisting gravitational collapse. The symmetry of orbital motion, which is circular rather than spherical, imposes its symmetry on the final shape. You can rotate a disk around its central axis and it looks the same, but you can't rotate it around any other axis without changing how it looks. This circular symmetry is a direct reflection of the circular symmetry of the orbital motion that supports it. Now, these giant disks of gas and dust don't stay uniform forever. Over time, the material in the disk starts to clump together. In some regions, the density becomes a bit higher than average, and these denser regions have stronger gravity, pulling in even more material. Eventually, you get large concentrations of mass forming within the disk. In the center, where most of the mass accumulates, you get a star forming. The density and temperature in the central region becomes so high that nuclear fusion ignites, and suddenly you have a brilliant new star burning in the heart of the disk. Further out from the center, smaller clumps form and grow, sweeping up the gas and dust in their orbital paths, eventually becoming planets. But even after all the gas has been cleared away, even after the star and planets have fully formed, the disk structure remains. The planets continue to orbit in roughly the same plane, the plane of the original disk. This is why our solar system is flat. This is why all the major planets orbit the Sun in nearly the same plane, and why that plane is also roughly aligned with the Sun's equator. You can see this same pattern repeated throughout the universe at every scale where rotation matters. When a star in a binary system pulls material off its companion, that material doesn't fall straight down onto the star's surface. Instead, it has angular momentum from the orbital motion of the binary system, and so it forms an accretion disk, a swirling disk of hot gas spiraling inward toward the star. These accretion disks can become incredibly hot and bright, sometimes outshining the star itself. Around black holes, where the gravitational field is so intense that infalling material is accelerated to nearly the speed of light, accretion disks can produce some of the most luminous objects in the entire universe. Quasars, the brilliantly glowing cores of distant galaxies powered by supermassive black holes, consuming vast amounts of material, get most of their light from these accretion disks. The disk is so hot that it glows across the entire electromagnetic spectrum, from radio waves to X-rays, and can outshine all the hundreds of billions of stars in the surrounding galaxy combined. And at the largest scales of all, we have spiral galaxies like our own Milky Way. These are enormous structures containing hundreds of billions of stars, countless clouds of gas and dust, and vast amounts of dark matter that we can't see directly but can detect through its gravitational influence. And despite their immense size, despite containing so much mass spread over such vast distances, spiral galaxies are fundamentally disk-shaped. The Milky Way is about 100,000 light-years across, but only about 1,000 light-years thick in most places. That's a ratio of 100 to 1, making it proportionally much flatter than a vinyl record. And this flat structure exists for exactly the same reason that our solar system is flat. The galaxy is rotating. All the stars and gas clouds are in orbit around the galactic center. And this orbital motion provides support against gravitational collapse in the plane of the disk, while allowing collapse perpendicular to that plane. The formation of a spiral galaxy follows the same basic process as the formation of a solar system, just scaled up enormously in both size and time. It starts with a large, diffuse cloud of gas, dust, and dark matter, rotating slowly due to whatever residual angular momentum was imprinted on that region of space during the early universe. As this cloud collapses under its own gravity, the rotation speeds up and the cloud flattens into a disk. But where a solar system might form in a few million years, a galaxy takes billions of years to fully develop. And where a solar system ends up with most of its mass concentrated in a single star at the center, a galaxy retains much of its mass distributed throughout the disk, gradually converting gas into stars over billions of years. The spiral arms you see in galaxies like the Milky Way are not permanent structures. They're actually density waves, regions where stars and gas clouds are temporarily bunched together as they orbit the galactic center. Imagine cars on a circular highway. Sometimes traffic slows down in certain areas, creating a jam. The jam itself might stay in roughly the same place, even though individual cars are constantly entering the jam from behind and leaving it from the front. The jam is a density wave, a region of higher density that persists even though the objects making it up are constantly changing. Spiral arms in galaxies work the same way. The spiral pattern persists and rotates slowly, while individual stars orbit through it much faster, spending some time in the bright spiral arm where star formation is active, then emerging from the other side and continuing their orbit through the dimmer inter-arm regions. So to summarize this second major insight, disks form instead of spheres when the dominant force resisting gravitational collapse is orbital motion rather than pressure. Orbital motion has circular symmetry, not spherical symmetry. It resists collapse in the plane perpendicular to the rotation axis, but does nothing to resist collapse parallel to that axis. This asymmetry in the supporting force creates an asymmetry in the final shape, resulting in flat, spinning disks rather than round, static spheres. Now let's step back and look at the bigger picture of what we've learned. We started with a simple observation. Space objects are either spheres or disks, and we wanted to know why. The answer, as we've seen, comes down to two fundamental concepts: equilibrium and symmetry. Equilibrium tells us that objects settle into stable configurations where all forces balance. Symmetry tells us what those stable configurations look like, because the symmetries of the forces that create equilibrium determine the symmetries of the shapes that result. Spherically symmetric forces create spherical shapes. Circularly symmetric forces create circular or disc shapes. It's a beautiful example of how the abstract mathematical properties of physical laws manifest as the concrete observable structures we see around us. But the importance of symmetry in physics goes far beyond explaining why planets are round and galaxies are flat. Symmetry is actually one of the deepest and most powerful concepts in all of physics, connected to some of the most fundamental laws of nature. There's a theorem, proven by the mathematician Emmy Noether in 1915, that establishes a profound connection between symmetries and conservation laws. Noether's theorem states that for every continuous symmetry in the laws of physics, there exists a corresponding quantity that is conserved, that remains constant over time. This might sound abstract, but its implications are staggering. Consider the symmetry of time translation. This is the idea that the laws of physics are the same today as they were yesterday and will be tomorrow. If you perform an experiment today and then perform the exact same experiment under the exact same conditions tomorrow, you'll get the same result. This is a symmetry because we can shift forward or backward in time and the laws of physics remain unchanged. And according to Noether's theorem, this symmetry of time translation corresponds to the conservation of energy. Energy cannot be created or destroyed precisely because the laws of physics are the same at all times. This is not a coincidence. These two facts, the unchanging nature of physical laws over time and the conservation of energy, are actually two sides of the same coin, connected by the deep logic of Noether's theorem. Similarly, consider the symmetry of spatial translation. This is the idea that the laws of physics are the same here as they are over there. If you perform an experiment in New York and then perform the same experiment in Tokyo, you'll get the same result, because the laws of physics don't depend on your location in space. This symmetry of spatial translation corresponds to the conservation of linear momentum. The total momentum of a closed system remains constant because the laws of physics are uniform throughout space. And here's where things connect back to our discussion of shapes. There's also a symmetry of rotation. The laws of physics are the same regardless of which direction you're facing. If you perform an experiment facing north and then perform it facing east, you'll get the same result. This rotational symmetry corresponds to the conservation of angular momentum, the very quantity that caused our collapsing gas clouds to spin faster as they contracted, ultimately leading to the formation of disks rather than spheres. Angular momentum is conserved because the universe doesn't have a preferred direction, because the laws of physics are rotationally symmetric. So the symmetries we've been discussing aren't just abstract mathematical properties. They're fundamental features of how the universe works, intimately connected to the most important conservation laws in physics. The fact that gravity has spherical symmetry isn't just a convenient mathematical fact. It's a reflection of the deeper truth that space itself has no preferred direction, that the universe treats all directions equally. And this deep symmetry of space is what gives us the conservation of angular momentum, which in turn governs the formation of disks, which determines the structure of solar systems and galaxies. When you look at it this way, the shapes of the largest structures in the universe are telling us something profound about the underlying symmetries of physical law. A spherical planet is a testament to the fact that gravity pulls equally in all directions, which is itself a consequence of the isotropy of space. A disk-shaped galaxy is a testament to the conservation of angular momentum, which is itself a consequence of the rotational symmetry of physical law. The shapes we see in the cosmos are, in a sense, visible manifestations of invisible symmetries, concrete expressions of abstract mathematical truths. This brings us to an even more mind-bending realization. These symmetries don't just shape the objects in the universe, they shape the very fabric of space-time itself. Einstein's general theory of relativity tells us that what we perceive as gravity is actually the curvature of space-time caused by the presence of mass and energy. A massive object like the Sun doesn't just exert a force on nearby objects, it actually warps the geometry of the space and time around it, and objects moving through this warped space-time follow curved paths that we interpret as gravitational attraction. And the degree and nature of this warping reflects the symmetries we've been discussing. A spherical, non-rotating mass, like an idealized planet, creates a spherically symmetric warping of space-time around it. At any given distance from the center, space-time is curved by the same amount in all directions. This is why gravity from such an object has spherical symmetry. The force field is spherically symmetric because the underlying geometry is spherically symmetric. A rotating mass, on the other hand, breaks this perfect spherical symmetry. The rotation causes space-time to twist slightly, an effect called frame dragging. The space-time geometry becomes only axially symmetric around the rotation axis, but not spherically symmetric. And in extreme cases, like a spinning black hole, this can lead to very exotic effects, including regions of space-time that are dragged around with the rotating mass. So even when we move from Newton's picture of gravity as a force to Einstein's picture of gravity as geometry, symmetry remains the central organizing principle. The symmetries of the mass distribution determine the symmetries of the space-time geometry, which determine the symmetries of the motion of objects through that space-time, which ultimately determine the symmetries of the structures that form. It's symmetry all the way down, connecting the abstract mathematics of geometry to the concrete physics of how matter behaves to the observable astronomy of what shapes we see in the sky. There's something deeply satisfying about this realization. The universe could have been arbitrary and chaotic, with different rules applying in different places or at different times, with structures forming in random, unpredictable shapes. But instead, we find deep regularities, consistent patterns, universal laws that apply everywhere and always. And these regularities arise from symmetries, from the fact that the universe doesn't pick favorites among directions in space or moments in time. This democratic treatment of all positions, directions, and times leads directly to conservation laws, which constrain how matter and energy can behave, which in turn determines what kinds of structures can form and remain stable. And we can see this principle at work not just in the largest structures like galaxies and solar systems, but also in the smallest. Atoms, the building blocks of all matter, have their own symmetries that determine their properties. The electrons in an atom occupy orbitals with specific shapes determined by the symmetries of the electromagnetic force and the principles of quantum mechanics. The simplest orbitals are spherically symmetric, just like planets. More complex orbitals have different symmetries, like dumbbell shapes or cloverleaf shapes, but all of them reflect the underlying symmetries of the quantum mechanical equations that govern electron behavior. Even the fundamental particles themselves, the quarks and leptons and force-carrying bosons that make up everything in existence, are classified according to their symmetry properties. The standard model of particle physics, our best current theory of how the fundamental forces work at the smallest scales, is built entirely on symmetry principles. Different types of particles are different representations of certain symmetry groups, and the interactions between particles are determined by what symmetries are preserved or broken in those interactions. Physicists searching for new theories that might go beyond the standard model, theories that could explain dark matter or unify all the forces of nature, are guided largely by considerations of symmetry. So symmetry truly does shape the universe on all scales of space and time, from the quantum foam of the Planck scale, trillions of times smaller than an atom, all the way up to the large-scale structure of the cosmos, with galaxy clusters and superclusters stretching across hundreds of millions of light years. And we can see this shaping with our own eyes when we look up at the night sky and see the round moon, the round planets, and know that we live in a spiral disk galaxy. These shapes aren't accidents, they're inevitable consequences of the symmetries built into the laws of physics. It's worth pausing to appreciate just how remarkable this is. Human beings, fragile creatures confined to the surface of one small planet, have managed to figure out why the universe looks the way it does. We've traced the shapes of the largest structures in existence back to fundamental principles of equilibrium and symmetry. We've connected the concrete reality of what we can see and measure to abstract mathematical concepts. We've found order in what could have been chaos, patterns where there might have been randomness. This is the power of science, the power of the scientific method applied patiently and rigorously over centuries. We observe, we question, we hypothesize, we test, we refine our understanding, and gradually, piece by piece, we build up a picture of how the universe works. And the picture we've built is not just a collection of disconnected facts. It's a coherent, interconnected web of understanding where each piece supports and illuminates the others. Knowing why planets are spherical helps us understand stars, which helps us understand galaxies, which connects to our understanding of symmetry, which connects to conservation laws, which connects to the fundamental structure of physical law itself. Every question we answer opens up new questions, deeper questions, questions about the nature of the symmetries themselves, or about what breaks those symmetries, or about whether there are even deeper principles underlying the ones we've discovered. For instance, we know that the universe had a beginning, the Big Bang, when all of matter and energy and even space-time itself came into existence about 13.8 billion years ago. In the earliest moments after the Big Bang, the universe was incredibly hot and dense, so hot that the fundamental forces we see today, which seem so different from each other, were actually unified into a single force. As the universe expanded and cooled, this symmetry was broken. The unified force split into separate forces. First, gravity separated out, then the strong nuclear force, then finally the electromagnetic force and the weak nuclear force separated from each other. This process of symmetry breaking, where a system that starts out highly symmetric settles into a less symmetric configuration, is responsible for much of the structure and diversity we see in the universe today. And we can see symmetry breaking at work in our disk formation story too. The initial gas cloud, before it starts collapsing, is roughly spherical, or at least roughly symmetric in all directions. It has the full three-dimensional symmetry of space. But as it collapses and rotation becomes important, this symmetry is broken. A specific direction, the axis of rotation, becomes special and different from all other directions. The system settles into a configuration with lower symmetry, circular symmetry around that one axis rather than spherical symmetry in all directions. This is spontaneous symmetry breaking, where the laws governing the system are perfectly symmetric, but the solution the system settles into is not. And it's this symmetry breaking that gives us the rich diversity of disk structures in the universe, from solar systems to galaxies to accretion disks around black holes. There's something almost philosophical about all this. We started with a simple question about shapes, about why planets are round and galaxies are flat, and we've ended up touching on some of the deepest questions in physics. What is symmetry and why does it matter? How do conservation laws arise and why are they universal? What is the connection between the mathematical structure of our theories and the physical structure of reality? These are questions that sit at the boundary between physics and philosophy. Questions that have occupied some of the greatest minds in history and continue to drive cutting-edge research today. And yet, for all the abstract mathematics and theoretical physics involved, we can see the answers to these questions with our own eyes every time we look at the moon, or watch the sun set, or gaze at photographs of distant galaxies. The universe is not hiding its secrets from us. It's displaying them openly, written in the shapes of the objects around us, if only we learn to read the language. And that language is mathematics, particularly the mathematics of symmetry and conservation, and equilibrium. Once you understand that language, even a little bit, the universe starts to make sense in a new way. You're not just seeing random objects scattered through space, you're seeing the inevitable consequences of fundamental physical laws playing out on cosmic scales. Consider the fact that we can predict what we'll find when we point our telescopes at distant parts of the universe. We've never been to other galaxies. We've never visited the gas clouds where new stars are forming. We've certainly never gotten close to a black hole or a quasar. And yet we can say with confidence that when we look at these distant objects, we'll see the same patterns we see nearby. Spiral galaxies in distant corners of the universe will be flat disks, just like the Milky Way, for exactly the same reasons. Planets orbiting stars dozens or hundreds of light years away will be spherical, just like Earth, because gravity and pressure work the same way everywhere. The laws of physics are universal, and so are their consequences. This universality is itself a kind of symmetry, a symmetry under translation from one location in the universe to another. And it's this symmetry that makes science possible in the first place. If the laws of physics were different in different places, if what was true here wasn't true there, then learning about the universe through local experiments would be pointless. We could never extrapolate from what we observe nearby to what happens far away. But because the laws are universal, because they respect this translational symmetry, we can observe processes happening in distant galaxies billions of light years away and understand them using the same principles we've learnt from experiments in laboratories here on Earth. And this brings me to the final point I want to make, which is about the nature of scientific understanding itself. We've covered a lot of ground in this exploration, from the mechanics of bridges to the formation of galaxies, from Newton's laws of gravity to Einstein's general relativity, from the quantum mechanics of atoms to the large-scale structure of the cosmos. But all of this understanding rests on a few simple principles: equilibrium, symmetry, and conservation. These aren't just abstract concepts that physicists find mathematically convenient. They're fundamental features of how the universe actually works, principles that we've discovered through careful observation and experimentation, and that we've verified over and over again in countless different contexts. And the beautiful thing is that these principles, once you understand them, make the universe comprehensible. You don't have to memorize separate explanations for why every individual object has the shape it does. You understand the underlying reasons, the deep principles, and then you can apply them to any situation. Why is Jupiter round? Because it's massive enough that gravity overcomes the structural strength of its material and pressure forces it into a sphere. Why is Saturn's ring system flat? Because the ring particles are in orbit around Saturn, and orbital motion creates a disk. You don't need someone to explain each case individually. You can figure it out yourself from first principles. This is what makes physics so powerful and so satisfying. It's not just a catalogue of facts about the universe. It's a framework for understanding, a set of tools you can use to make sense of what you observe. And the more you learn, the more connections you see, the more deeply you understand how everything fits together. The shape of a planet is connected to the properties of materials under compression, which is connected to the electromagnetic forces between atoms, which is connected to quantum mechanics, which is connected to the deepest symmetries of space-time itself. Everything is connected, and understanding one piece helps you understand all the others. And we're not done. There's still so much we don't understand about the universe. We don't know what dark matter is, the mysterious substance that makes up most of the mass in galaxies but doesn't emit light. We don't know what dark energy is, the even more mysterious force that's causing the expansion of the universe to accelerate. We don't have a complete theory of quantum gravity that can explain what happens at the centers of black holes or in the first moments of the Big Bang. We don't fully understand how galaxies form and evolve over billions of years, or how planetary systems like our own come to have the specific properties they do. But we have the tools to investigate these questions. We have the principles of equilibrium and symmetry to guide us. We have the conservation laws that constrain what's possible. We have the mathematical frameworks of quantum mechanics and general relativity that have proven incredibly successful in their respective domains. And we have the scientific method, the process of careful observation, rigorous testing, and constant refinement of our theories. Slowly, question by question, experiment by experiment, observation by observation, we're filling in the gaps in our understanding, building a more and more complete picture of how the universe works. And every once in a while, we take a step back and appreciate how far we've come. We started this journey with a simple question: why are space things the shapes they are? And we've discovered that the answer connects to nearly everything else we know about physics. Spheres and disks, planets and galaxies, atoms and conservation laws, all tied together by the elegant mathematics of symmetry. The universe really does seem to love these two particular shapes, and now we understand why. It's not arbitrary or random. It's inevitable, a direct consequence of the symmetric laws of physics operating on matter under the influence of gravity and orbital motion. So the next time you look up at the moon and see its perfect round face, or look at a picture of a spiral galaxy and see its graceful disk shape, you'll know that you're not just seeing a random shape that happened to form. You're seeing the visible signature of invisible symmetries, the concrete manifestation of abstract mathematical principles, the inevitable result of universal physical laws. You're seeing the universe expressing its deepest nature through shape and form. And that, I think, is truly beautiful. The cosmos is not just vast and ancient and mysterious. It's also comprehensible, structured, governed by principles we can discover and understand. And that makes it not less wondrous, but more so. Because now when we look at the stars, we're not just seeing lights in the sky. We're reading messages written in the language of physics, messages that tell us how the universe works, why things are the way they are, and how everything connects to everything else. Symmetry really does shape the universe on all the scales of space and time, from the quantum realm to the cosmic horizon. And now you understand why.